Welcome to your video notes for section 1.1 through 1.4. So today we're going to start going through your Unit 1 packet. Some of these things you guys have seen in your summer assignment, but we're going to be reviewing moles and molar mass. And then something that was not on your summer assignment, we're going to talk about mass spectroscopy today in your notes, and then also composition of pure substances. 1.4, the mixture compositions, we're going to continue on with that when we come back to class. So what you guys need for this video section of notes, you need your notes packet, you need your periodic table, and you need your calculator to work through some calculations. So let's go ahead and get started. Okay, so we're going to go ahead and start with some things that are a review from what you guys did on your summer assignment. So we're going to start with just simple mole conversions using Avogadro's number and also calculating molar mass. So let's just go through a couple of things here. First, we have our conversion factor. When we're talking about moles in chemistry, we're going to use that a lot more than we use how many atoms or how many molecules and things like that, because when we have reactions, we have lots of molecules reacting. And so in order to take that into account, we use moles as a unit to represent how much we have of something in a chemical reaction. So our conversion factor for that, you guys saw this in your summer assignment, 1 mole equals 6.022 times 10 to the 23rd atoms or molecules. It can be either one. So we're going to use that as a conversion factor, and in some dimensional analysis, we'll use that as our conversion factor. Molar mass is going to be what is the mass in grams of 1 mole of a substance. So for that, we're going to be looking at our periodic table. If you guys find carbon on your periodic table and the mass that's listed below that, you'll see that the mass of carbon is 12.01 grams. We're going to use that also as a conversion factor. I'll go through some examples here in just a minute. Okay, first equation that we're going to come across, which is on your reference sheet for the AP exam, which means that it'll be given to you on any exam that you guys take in here, is this equation. You need to know what all of these things represent, what they stand for, and how to use the equation. Okay, so first of all, anytime you see lowercase n in an equation, it's going to represent the number of moles. So when we're calculating number of moles, a lot of times we're going to do that using dimensional analysis, but this equation is something you can use as well, depending on the information that you're given. So M is going to be our mass in grams, and capital M is going to be our molar mass, which we find by looking on the periodic table. And again, we'll do an example of this. Another common thing that you're going to have to do with this equation is to be able to rearrange it to solve for the capital M molar mass. And when you rearrange this equation to solve for the molar mass, that's going to be the mass in grams divided by the number of moles. Because when you calculate molar mass, we're calculating that in units of grams per mole. So we'll be able to use this equation to help us out calculating all of those different things. All right, so let's go ahead and go through our first example here. So this question says, how many atoms are in 10 grams of lead? So we have a couple of conversions that we have to do. So first of all, there is no conversion that goes straight from grams to atoms. That conversion factor doesn't exist. So what we have to do instead is we have to go from grams to moles to atoms in 2 conversion factors, and we're going to set that up with our dimensional analysis. So first of all, if we find lead on the periodic table, the molar mass for lead is 207.2 grams per mole. And if I use that as a conversion factor, it means that I have 207.2 grams in 1 mole of lead. So here's how I'm going to set up that dimensional analysis. I'm going to start with what I'm given in the problem, which is my 10.0 grams of lead, and I'm going to set up all of my dimensional analysis the way we did in the previous unit. And the first thing I want to cancel is my grams of lead. So I'm going to take this unit of grams per lead and I'm going to put it down here in the diagonal right box, and I'm going to convert that into moles first. So I want to go from grams of lead to moles of lead. The molar mass that I find on the periodic table, which is 207.2, that's going to go right here, and that's how many grams I have in 1 mole of lead. Setting that up is going to cancel out my grams of lead units, and now I've converted from grams of lead to moles of lead, and my next step is going to be to convert from moles of lead to atoms of lead. This is where we're going to use Avogadro's number, where we have 1 mole equals 6.022 times 10 to the 23rd. This can be atoms or molecules or really anything. For this one, we're asked for atoms. So 1 mole of lead, it can be 1 mole of anything, is equal to 6.022 times 10 to the 23rd atoms of lead. So that's going to cancel out my units of moles of lead and leave me with atoms of lead, which is what I'm looking for. Okay, just kind of a heads up with your calculators. I do want you guys to go ahead and take the time to plug this in and make sure that you know how to plug this in correctly in your calculator. When you're plugging in Avogadro's number into your calculator, make sure that you're using parentheses, and you can do that a couple different ways. You can plug it in, it depends on your calculator. You can plug it in like this. As long as it's in parentheses, it'll keep it together. Or if you have a calculator that has an EE button, you can push that button right here and put 23, and that'll tell your calculator times 10 to the 23rd, and it'll show up as just 1 E on your calculator, I believe. When you go ahead and plug all that in, so you're going to multiply your numbers across the top, 10 times 6.022 times 10 to the 23rd, making sure that's in parentheses, divide by the molar mass of 207.2, and you get an answer of, you should get 2.91 times 10 to the 22nd atoms of lead. Okay, so we had 2 different conversions that we had to work with there. Our molar mass, this right here was our molar mass, and our Avogadro's number conversion factor that we needed to use for that. Okay, in our previous question, we used the molar mass of lead, and so that was just one thing that we found on our periodic table, but we also have to be able to use molar masses for compounds or molecules that have multiple atoms as part of them. If that's the case, all you have to do is add everything that's there. So if we look at this formula of aluminum nitrate, the first thing I want to do is I want to think about how many of each one of those things do I have. So I have 1 aluminum. I have the 3 on the outside of the parentheses goes to everything on the inside. So that means that I have 3 nitrogens and I have 9. I'm going to multiply those subscripts together, 9 oxygens. So when I'm finding my molar mass of aluminum nitrate, I need to find aluminum, nitrogen, oxygen on the periodic table, find those molar masses, and multiply them by how many of each one I have, and just add them together. So 1 aluminum, when I find aluminum on the periodic table, that has a molar mass of 26.98, and nitrogen has a mass of 14.01, so I'm just going to multiply that by 3. And then oxygen has a mass of 16.0, and I'm going to multiply that by 9. And then everything just gets added together, and I get my molar mass of aluminum nitrate is 213.01 grams per mole. That means if you have 1 mole of aluminum nitrate, it's going to have a mass of 213.01 grams. All right, let's go on to our next example. Our next example is asking us how many hydrogen atoms are in 72.5 grams of C3H8O. So first of all, what I want to do is I want to figure out the molar mass of C3H8O. So if I add up 3 carbons, 8 hydrogens, 1 oxygen, I'm going to end up with 60.11 grams per mole as my molar mass of that compound or that molecule. The other thing I want to recognize is if I have 1 mole of C3H8O, basically for every one of those, I have 8 hydrogens. So if I have 1 mole, then I'm going to have 8 moles of hydrogen. That ratio is there because of this subscript. So we're going to use that in our calculation. So I'm going to go ahead and start my calculation here with what I'm given. So I have 72.5 grams of C3H8O. And my first step is going to be to cancel out grams of C3H8O. So, and convert that into moles. In order to convert from grams to moles, anytime you convert from grams to moles, you're going to be using the molar mass. So that means my molar mass that I found up here earlier, 60.11, is going to go in that box. And that's how many grams are in 1 mole. So I get grams of C3H8O to cancel. And then I want to convert, since I'm looking for just hydrogen, I'm not looking for C3H8O, I need to convert the molecule into just hydrogen atoms. That's where I'm going to use this conversion factor right here. So for every 1 mole of C3H8O, I have 8 moles of hydrogen. So then those 2 units cancel out. And then I want hydrogen atoms, so 1 mole of hydrogen. Anytime you're doing moles to atoms, this is where you use Avogadro's number. .022 times 10 to the 23rd. Okay, so there, moles of hydrogen cancel, and I get atoms of hydrogen. So I can go ahead and calculate by multiplying everything across the top and dividing by the number on the bottom. Go ahead and plug that into your calculator to make sure that you do that correctly. You should end up with an answer of 5.81 times 10 to the 24th atoms of hydrogen. All right, for this next section, we're talking about something called mass spectroscopy. So first of all, in order to understand what's going on with mass spectrum graphs that we're going to be looking at, we need to understand and know what an isotope is. An isotope is an atom of the same element with different numbers of neutrons. So first of all, let's talk about what you see on the periodic table. If you look up fluorine, for example. Sorry, I was finding a good one. So fluorine on your periodic table, it has atomic number of 9, and it has a mass number of 19 if you round it. On your actual periodic table, it says 18.998. That's an average number. This top number is our atomic number, and it tells us the number of protons. So that means fluorine has 9 protons. It also tells us the number of electrons if we're dealing with neutral atoms, which for now we are. Protons are positively charged, electrons are negatively charged. In order to find the average number of neutrons, we subtract 19 minus 9, so there are 10 neutrons in the nucleus. Neutrons are neutral, they don't have any charge. So most of the fluorine atoms have 10 neutrons, but not all of them have 10 neutrons. Some of them can have different numbers of neutrons. That's why when you look on the periodic table, you get a number that actually looks like this, 18.9984. That's because this is an average number based on all of the isotopes. And so we're going to talk about how they figure out what the average atomic mass is using the different isotopes of the elements. Okay, so isotopes have different numbers of neutrons. Let's see. So here's what happens with mass spectroscopy. They take a sample of all of the isotopes. So here we're starting with magnesium atoms, and it's a mixture of all the isotopes that are in there. It takes that sample and it ionizes it. So step number 1 is to take those magnesium ions or magnesium atoms and turn them into ions. And in order to do that, they lose electrons, they become positively charged. And then step number 2 is there's a section where it takes those magnesium ions and it accelerates it towards this area right here. So step number 3 is deflection. Deflection is basically where it can deflect the ions in a certain direction, and there's a certain amount of deflection depending on the mass. So different deflection for each mass or each isotope. And then once those isotopes, this is basically where they get separated in the deflection section. They could probably also call that separation, where they separate the different isotopes. And then it gets to section 4, which is to detect all of the different isotopes that are part of that sample. So once it's gone through the mass spectrometer, then you're going to end up with a graph. And let's take a look at what that graph looks like. Okay, so once you get to the detection section, all of the different isotopes show up on a graph, and each line represents a different isotope. So for this particular graph, there are 3 different isotopes. And what they can do, each line represents a different isotope. What they can do is it'll separate that substance, and for this particular one, it'll show that 79% of all of the atoms had a mass of 24. 10% had a mass of 25, and 11% had a mass of 26. Okay, so what we're going to do from there, in order to calculate the average atomic mass using the mass spectrum graph, we're going to take those percentages and we are going to turn them into decimals. And I'm going to multiply it by the mass. So basically my first isotope has a mass of 24, and 79% of all of my isotopes have that mass. So I'm going to take my 79% and I'm going to turn it into 0.79, and I'm going to do the same thing with all 3 isotopes. So my other isotope has a mass of 25. That should be 25. And I'm going to multiply that by the percent turned into a decimal, so that's 0.10. And I'm going to multiply that together, and I'm going to do this for all the isotopes and then add them together. So then my next isotope has a mass of 26, and that percentage is 11. Turn that into a decimal. We go ahead and we do this calculation, and you get 24.32. And this is the average atomic mass of magnesium. If you look on your periodic table, you should see, this is based on the data that was given to us in our graph here, but you'll see that the mass on the periodic table for magnesium is 24.3. So our periodic table values are just averages of all of the different isotopes. All right, let's go ahead and move on to the next section. Let's talk about percent composition and then empirical formulas. I don't know if percent composition was on your summer assignment or not. I can't remember. But basically, when we deal with molecules, ionic compounds, covalent compounds, just some terminology. When we use the word molecule, we're talking about covalent compounds. Those are all nonmetals. When we use the term formula units, we're talking about ionic compounds, which is when we have a metal and a nonmetal. So just a review of some terminology there. So if we're looking for percent composition, it's fairly simple. It's just like calculating the percent of anything. So we're going to look at percent composition of C2H6. The first step, anytime you find the percent of anything, percent is going to be how much do you have of the part that you're trying to find the percent for, and then divide it by the whole thing, and then you're going to multiply it by 100 to convert your decimal into a percent. So let's say I want to find the percent carbon in C2H6. My first step is to figure out what my total molar mass is. Okay, so if I have 2 carbons, I have 2 times 12.01. So 12.01, I get that from my periodic table, looking up carbon. And then I've got 6 hydrogens, so 6 times, and then looking up hydrogen on my periodic table, I have 1.008. Total, that gives me 30.068 grams of C2H6, but I want to know what percent of that is carbon. So if I just take the carbon, which is 2 times 12.01, that is 24.02, and I divide that by the whole thing, and then I can take that number and multiply it by 100. That will give me a percent. So I get 79.89. So basically what that means is that carbon is 79.89% of that whole compound. If they just ask you to do percent composition, then you'll calculate percent for both. So you can do it the same way, or you can just subtract from 100 to get the percent of hydrogen. All right, the next section, and this is going to be our last section, is to be able to calculate empirical formulas. So empirical formulas are the lowest ratio. So we're talking about basically the reduced formula. We talked about reducing formulas when we talked about naming compounds. And when we did that, and we had subscripts that look like this, 2 and 6, we can reduce those just like we would reduce fractions. So you can divide each of those subscripts by 2 and end up with CH3, which would be your empirical formula for C2H6. So you have to be able to simplify those, and then also we have to be able to calculate them depending on information that we're given. So let's take a look at an example for that. Okay, so in some of our empirical formula examples, we're going to be given percentages. Okay, so in this problem, I'm given that I have a compound that is 30.46% nitrogen and 69.54% oxygen, and I need to determine the empirical formula. These should be arrows here. So there's a set of steps that we're going to go through to calculate and figure out what that empirical formula is. So step number 1 is just to take your percentages, and we're going to pretend like we have 100 grams of this substance. So if I have 100 grams of this substance and 30.46% of it is nitrogen, that means I have 30.46 grams of nitrogen, and then I have 69.54 grams of oxygen. Okay, so that's step 1, is just to convert those over. So if you're given percentages, do that. If they give you grams to start with, then you don't have to do step 1. You just go straight into step 2. Step 2 is to go ahead and convert from grams to moles. So find my molar mass of nitrogen, which is 14.01 grams. Do the same thing with oxygen. That's 16 grams in 1 mole. This is going to give me my number of moles of each one of those things. So I have 2.17 moles of nitrogen, and I have 4.35 moles of oxygen. Okay, that's step number 2. Step number 3 is to take the smallest amount of moles, which in this case is 2.17, and divide each number by that. What that does is it gives you a ratio of how those things react together to form a compound. So these two numbers become your subscripts in your formula. So my subscript for oxygen is going to be 2, my subscript for nitrogen is going to be 1. So I'm just going to have NO2 is going to be my empirical formula for that substance. If you get a number, when you do step 3 and you divide by the smallest mole amount and you get the 1 and the 2 here, let's say you got something like 1.5 and 2. Well, you can't have subscripts that are decimals. You can't have 1.5 as a subscript. So what you're going to have to do is multiply that by 2 so that it gives you a whole number. But you can't just do that. If you multiply one of the subscripts by 2, you have to multiply the other subscript by 2. So then you'll end up with 3 and 4 instead of 1.5 and 2. Same thing if you end up with something that ends in 1.33, then you have to multiply it by 3 to give you a whole number, and you'll have to multiply both of them by 3 in order to get the subscripts. So keep in mind, if you get a number over here with your calculations that isn't a whole number, that you can multiply them by something to get a whole number for your subscripts, for your empirical formulas. Okay, so hang on to these notes, bring them back with you to class, and then there's a section, the next page in your notes is for practice. We're going to do that at the beginning of class tomorrow, so you don't need to do that now. All right, so I'll see you in class.